Going back the other way, integrating our trig functions. If it's a cosine of a linear function, well then it'll be 1 over a, so dividing by the derivative if you like, the sine. So now cosine, this is where we've got to be really careful, because when we differentiate cosine we get negative sine, but when we integrate cosine we get positive sine. And the same sort of thing happens with the sine function. When we differentiated sine we got cosine, but when we integrate sine we'll get negative cosine. And, well, integral of sec squared then goes to tan, because sec squared goes to tan. So if I want to integrate sine 3x, then sine now goes to negative cosine, so minus a third cosine of 3x. Cos now goes to sine, but the coefficient of x here is negative 5, so we end up with negative 1/5 sine 1 minus 5x. To complete the set, let's do a sec squared one. Sec squared goes to tan, the reciprocal of a half is 2. Let's do a definite integral. Now this is where it's really important too, radians. Whenever you're doing calculus with trig functions, radians is the angle measure that we use. Because remember how we proved the results? We used that theorem about half r squared theta and so on. The angle was measured in radians. So got to have radians for it to work. Minus a half cos 2x, when we integrate, we're going from pi on 6 to pi on 2. Cos of pi, I'm thinking of my graph here, starts up there, that's negative 1 cos of pi, and pi on 3, ooh, exact value, pi on 3 is 60 degrees, cos of 60 is a half, I think. Okay, so we get 3/4. Ooh, but what if it's not linear? Okay, now we want to go back to the idea of, can we set it up in the format we know how to deal with? So I want derivative times the trig function and then whatever the angle. Well, the angle here is x squared. So I would like the derivative of x squared out the front, which would be 2x. I've got 1x. So I've got a half of that. But once I've got it in that form of derivative times the function, I know that's going to go to tan. Sec squared goes to tan. So I've got a half tan x squared plus a constant. Sine squared, now watch out. There's always going to be in the extension 1 paper, the HSC, can't even remember a year where it was never asked somewhere, integrating sine squared or integrating cos squared. Why? This is where the double angles come in again. Cos 2 theta, remember the different ways we could write it. We could write it as cos squared minus sine squared. I could also write it in terms of just sine squared, so 1 minus 2 sine squared. If I make sine squared the subject, I get a half of 1 minus cos 2 theta. And for cosine, well, I end up with cos squared as a half of 1 plus cos 2 theta. It allows me to do these integrals. So sine squared, that goes to a half of 1 minus cos 2x. I can integrate both of those. So the 1 goes to x, the cos goes to sine, so we get minus a half sine 2x. We have our answer. You can always guarantee you're going to get one of those. Well, what about tan? We didn't talk about tan. Okay, how do we integrate tan? Well, tan, I can rewrite as sine on cos. I now have derivative on function. Well, almost. The derivative of cos is, of course, minus sine. So I've got minus that. So it's minus the log of cos x being in absolute value there. Of course, there's another way you could write that, because remember with logs, that minus 1, I could bring it inside the log, so it's cos x to the power of negative 1, which is 1 over cos x. The reciprocal of cos is sec x. So a lot of people tend to say log of sec because we prefer the positive rather than the negative. It doesn't really matter. I mean, both are correct. Cos x sine to the power of 7x. Again, we want it in the form that we used to. I want derivative times the function, and the derivative of sine is cos. So I do actually have that. Now, if you don't see it straight away, look at this substitution. If I made u equal to sine x, then du becomes cos x. I've got to change the limits, of course. Now, when x equals 0, u equals 0. When x is pi on 2, u equals 1. And it just becomes u to the power of 7. So add 1 to the power, over the power, sub in, we got it. If you spot it straight away, and you see, hang on a sec, I've got it in that form of derivative times some function to the power of n, remember that rule? If I spot it, great, I'm going to use that. Yeah. Okay. Now, The difference, I suppose, is in extension 1, they do like to give you the substitution. Now, if they tell you using this substitution, you've got no choice. You've got to use that substitution. But if they don't tell you, then you can do it whatever way you like. Here's a 2020 paper. They asked this one. 0 to pi on 2 cos 5x times sine 3x. There is no way I'm going to be able to write that as derivative times the function because the angles are different. So this is playing with our product to sum idea. So there it is. 2 sine cos goes to sine a plus b plus sine a minus b. So we can rewrite that now. And I get 2 functions that I can integrate. So the first one, well, notice the formula is sine cos, not cos sine. That's important for when you're working out the difference. The sum, it doesn't matter because you can add them in any order, but obviously you can't subtract in any order. So it's got to be the sine one that starts. So it's 3x minus 5x. That's why we've got sine of minus 2x. I changed that because sine's an odd function to be minus sine 2x. Now let's integrate those. Minus an 8 cos 8x plus a half cos 2x. Substitute in pi on 2, substitute in 0, and we come up with our answer. Okay. That shall do us.